Hello. In the next few videos, we're going to be looking at the expectation operator. The expectation of a random variable is enormously important as it is central to the way in which we interpret any probability distribution function. In other words, we need the expectation operator if we are to make any connection between our probabilistic models and the results from experiments. Before we get onto that though, in this video our focus is going to be on how the expectation of a random variable is calculated. Consequently, by the end of this video, you should be able to calculate the expectation of a discrete random variable from the probability mass function and explain how the expectation of a continuous random variable can be calculated from the probability density. Let's start this process by briefly reviewing what we have learnt in other videos. The first thing we have learned is that when we do experiments that generate numerical data, we use random variables to describe their outcomes. There are two types of numerical result we might get from an experiment, and as such there are two types of random variables. When we do the first type of these experiments, we get one from amongst a set of mutually exclusive outcomes. I am thinking here of our now infamous game of blind man's bluff. We describe each of the outcomes of such an experiment using a discrete random variable, and thus ascribe a single integer to each of the possible outcomes. So in this case, we use 1 to represent the fact that we selected Stephen, 2 for Conrad, and 3 for Maeve. To describe the probabilities of each of these outcomes, we introduce a function known as the probability mass function that tells us the probability that the random variable from our experiment is equal to, in this case, 1, 2, or 3. If you want, we can think of this probability mass function as a 3-component vector in this case, and thus label the probability of selecting Stephen as P1, the probability of selecting Conrad as P2, and the probability of selecting Maeve as P3. The other types of experiments we do generate a random variable between some upper and lower bound. The number generated here is a real number, and there are an infinite number of outcomes for these types of experiments. For these continuous random variables, we showed in our video on probability distribution functions that we can obtain a probability distribution function that is in some way analogous to the probability mass that we had for discrete random variables by taking the derivative of the cumulative probability distribution function. The resulting function is known as the probability density. The analogy between the probability density and the probability mass comes in the way that we can convert our probability mass/density function to a cumulative probability distribution function. Because the various outcomes for our discrete random variable are all mutually exclusive, we can calculate the probability that the random variable equals 1 or 2, i.e. that it is less than or equal to 2, by adding together the probability that it is equal to 1 and the probability that it is equal to 2 as shown here. In other words, if we want to calculate the cumulative probability distribution function, we do a sum over the elements of our probability mass as shown here. If we go to the continuous limit and deal with a continuous random variable, this summation is replaced by an integral. We can thus calculate the cumulative probability from the probability density using the following integral. Having reviewed this background material, let's now turn to the expectation operator. In some ways, this operator is similar to a function. Much like a function, it takes something as input and outputs a number as shown here. The difference, though, is that whereas the argument of a function is a number or some small set of numbers, the argument of an expectation operator is a random variable. A random variable is a much more complicated object than a number or a small set of numbers. As we have learnt in these videos, a random variable has an associated cumulative probability distribution function. It also has a set of values it can take, and if it is a discrete random variable, it has a probability mass function. Any operator on this object thus has many things that it can play with when it generates the output number. A function, by contrast, can only play with the input arguments. With all this in mind, the expectation operator is defined as shown here. The sum runs over all the possible values that the random variable can take. The xi values within this sum are then the values the random variable can take. In most cases, when you see the expectation operator written like this, the first xi value will be 1, the second 2, the third 3, and so on. The pi's are then the probabilities of getting each of these outcomes. In other words, these are the various elements of the probability mass function / vector. I should point out at this stage that this is the expectation operator for a discrete random variable. To make this process completely clear, let's look at an example calculation of an expectation for our blind man's bluffs experiment. As we have discussed now on many occasions, we use an integer to represent each of the possible mutually exclusive outcomes from our experiments. These are our xi values. We then have a probability of getting each of the possible outcomes, P1, P2, and P3 in this case. We then take the sum of the product of xi and pi, and thus find that in this example the expectation is equal to 1 times P1 plus 2 times P2 plus 3 times P3. Now it is important to note that this quantity may or may not be an integer. The expectation is thus not the most likely outcome of the experiment. In fact, it may not even be one of the outcomes from the experiment. We will come back to that again, though, in the videos on the law of large numbers and the central limit theorem. Hopefully you found the last slide relatively straightforward. On this slide, we're now going to add one further complication, but it will be not made much more difficult. Rather than calculating the expectation of the random variable, we're going to calculate the expectation of a function of the random variable. For this first example, we're going to use the linear function g of x equals ax plus c. Before we get into doing this calculation, however, let's just clarify what we mean by talking about a function of a random variable. Essentially, we are imagining that we are doing some experiment that has a random outcome, and here we're going to represent this experiment as the arrival of a comet that could hit Stephen, Conrad, or Maeve. The person it hits is random. When I perform this experiment here, you see that the comet hits Maeve. The result from the random experiment, a random variable, capital X, is thus equal to 3. Hence 3 is inserted into our formula, and the final result of the experiment plus function is 3a plus c. Now, if we wanted, we could use the formula that we had previously used to calculate the expectation to calculate the expectation for this process of random experiment plus function. Our xi values in this case would just be x plus c for Stephen, 2x plus c for Conrad, and 3x plus c for Maeve. It is far more common, however, to write the expectation of a function of a random variable in this way. We now have that xi is 1 for Stephen, 2 for Conrad, and 3 for Maeve. G of xi, meanwhile, is x plus c for Stephen, 2x plus c for Conrad, and 3x plus c for Maeve. Now, remembering that the probabilities of picking Stephen, Conrad, and Maeve are P1, P2, and P3 respectively, we can obtain the final expectation of g of x as a plus c multiplied by P1 plus 2a plus c multiplied by P2 plus 3a plus c multiplied by P3. Grouping terms in a and c, we then get to the following expression. Look at this expression though. P1 plus P2 plus P3 is the probability of picking Stephen, Conrad, or Maeve. In other words, it is the probability of picking one of the 3 possible mutually exclusive outcomes from our experiment. This is just equal to 1 by normalization. Similarly, for the first term, we have 1 multiplied by P1 plus 2 multiplied by P2 plus 3 multiplied by P3, which, as we learned on the previous slide, is just the expectation of our random variable capital X. We thus arrive at the following generic result for the expectation of a linear function of a random variable. The expectation of the function ax plus c is equal to a multiplied by the expectation of of the random variable plus c. This result is hugely useful, as we will see, but importantly, it only holds for functions that are linear in the random variable. Consequently, it will not hold if we're taking the square of the random variable, as we will now show. Remember that the xi values for Stephen, Conrad, and Maeve are 1, 2, and 3 respectively. Their squares are thus 1, 4, and 9. The expectation of the random variable X squared is thus p1 plus 4p2 plus 9p3, which cannot be written in terms of the expectation of X. This process of taking the expectation is hugely important, and this process of taking expectations of functions of the random variable even more so. It is so important, in fact, that we have special names for some of the expectations of functions that we can calculate. So, for example, if we take the expectation of the nth power of the random variable, this is a quantity known as the nth moment of the distribution. If, by contrast, we take the random variable, subtract its expectation, and then raise this final quantity to the nth power, and then take the expectation, we arrive at a quantity known as the nth central moment. The second central moment is a particularly important example of an nth central moment, and it is known as the variance. It is relatively easy to show, I will leave it as an exercise, that the variance can be calculated in either of the two ways shown here. We can even have expectation values that are themselves functions. A particularly important one of these is known as the moment generating function m underscore x of t. This is calculated as shown here. You take the expectation of e to the t, which is the parameter of the moment generating function, and this is multiplied by the random variable X. The moment generating function is known as the moment generating function because if you take the nth derivative of this function with respect to t at t equals 0, this is equal to the nth moment. As you will see in some of the exercises, this makes this function very useful when it comes to calculating the expectation of certain types of random variables. To summarize, we have arrived at the following expression for calculating the expectation of a function of a discrete random variable, one where the random variable takes on only integer values. We now need to finish by introducing a similar expression for calculating the expectation of a continuous random variable. That is to say, a random variable that can take as its value any one of the real numbers between some lower and upper bound, 0 to 1 in this case. We do so by remembering that as we go from the discrete to the continuous limit, summation signs are replaced by integrals, and probability mass functions are replaced by probability densities. An example of this was when we noted that the cumulative probability distribution function can be calculated from the probability density by solving this integral. Doing a similar thing for the expectation operator, we thus find that the expectation of a function of a continuous random variable can be calculated by solving the following integral. So in summary, in this video we have introduced the following two equations. The first tells us that we can find the expectation of a discrete random variable by calculating the following summation. The second, by contrast, tells us that we can calculate the expectation of a continuous random variable by solving this integral. Sometimes these integrals have finite values, and sometimes they have infinite values, similarly for the summation. Through your project work, you will have opportunities to do these things for yourselves and see how these formulas are used in actuality. For the most part, in doing so, you are simply using calculus that you learned either at A-level or on the Level 1 course. For now, all you need to do is learn these formulas and understand how they are applied. I hope you managed to get that from this video. If not, please try watching it again. Thank you.